We've been mentioning anisotropic materials for a while, or anisotropic material behavior in general versus isotropy, and now it is time to mention what that explicitly means. In general, everything that we'll be doing in this course could be cast in the context of anisotropy. Our starting point, just like in the case of elasticity, is isotropy, and then we did thermoelasticity also in isotropy, and now we're going to do elasticity only in anisotropy. And then this way we could generalize, say, thermoelasticity to anisotropy, and I briefly mentioned what the corresponding effect would be, namely you'd get, say, shear deformations under temperature changes. This way we could also generalize everything else that we would be discussing in the future towards anisotropy as well, which we're not going to do. But I will mention once in a while what the consequences of anisotropic response would be. Only in the case of elasticity, we will be very rigorous about the characterization, let me say, of elasticity, of anisotropy. And the first thing we'd like to do is, well, we have stress, it has 6 components, and we have strain, it has ultimately also 6 components. And in the case of isotropy, we know how they're related to one another, but that's a very specific relation. In that relation, what we have is that normal stresses only influence normal strains, and shear stresses influence only shear strains. Now that's a notion that we'll have to discard in the context of anisotropic material behavior. And to make that discussion, therefore, where any component of stress could influence any component of strain and vice versa, it is inconvenient to introduce a notation through which we can easily relate various components of stress to various components of strain. And that's called the Voigt notation. And the Voigt notation, what it does is, it takes the components of a matrix, in particular in this case, let's say we start with the stress as a matrix, and it puts it in the form of a array or a vector. A vector, not in the sense that the components of this array transform like a vector, like the position vector. You change the coordinate system, it changes in a certain way the components of the position. So this is not really a vector, but we're going to call it a vector just for the present discussion. And that vector will have 6 components. It's going to be a 6x1 vector. And we will just cut that vector through 2 because there are distinct components to the stress vector, and that is going to be first the set of normal components, sigma x, sigma y, sigma z, and then the set of shear components. Okay, and the way we're going to think about the shear components is a usual sort of right-hand rule. So let me write the so this would be the usual right-hand rule. You cross x with y, you get z, z cross x, you get y, type of thing. And what we are going to do is we're now going to take the 6 independent components of the stress, because it's symmetric, and we're going to put it in there. We've already put the normal components. They're the diagonal components of the stress matrix. And then I'm going to put the shear. And there's a particular order that we will prefer. And the way the order goes is, well, we'll first start with, so there are 3 components, and the last 2 that I considered are y and z. So I'm going to sort of go in order, x, then y, then z. Then I've looked at y and z, those are the last 2. So first I'm going to put y and z. So y and z is sort of like these 2. Okay. Since I put y and z now, then I'm going to go in the order of this right-hand rule. So next I'm going to put tau zx, and then I'm going to put tau xy. So tau sigma x, y, z, and then the shear components in the corresponding manner that I've described. So similarly, we will put also the strain into the form of a vector or an array of 6 independent components. Now, we could have written, as I mentioned earlier, the strain also as a matrix. We never really did. So I'm directly writing the components of this array. And so the argument is going to go in the same fashion. So we first put the normal components, epsilon x, epsilon y, epsilon z. And then we go ahead and write first the last two, which is going to be in this case gamma yz. That's the shear component. And then I've written yz, then I go in order zx, xy. Okay. So that's one way to remember, although you don't really have to memorize the order of these things. Okay, well, so now what I would like to imagine is a scenario where I would like to be able to relate any components of stress to any component of strain, right? So I want to discard the notion that only normal stresses affect normal strains and only normal stresses affect the only shear stresses affect the shear strains, and in particular the notion that only tau yz affects gamma yz, etc. Perhaps these also affect gamma yz, perhaps these also affect gamma yz. So I want to look at this as a mathematical setting. Earlier I would write the epsilons on the left, or the shear on the left, and I would write the stresses on the right. So again I will have the shear on the left, the strains, I'm sorry, on the left, and I will have stresses on the right. Okay, I like to relate the two. But now I am writing everything compactly instead of one by one. I'm writing all the possible components of stress in there, all the possible components of strain, they are in here. So now this is 6 by 1 set of variables. This is another set of 6 by 1 variables. And I would like to figure out how these two are related to each other. So let me ask you a question. If I have a set 6 by 1 of variables and another set 6 by 1, what would be the most general way to relate the two to one another? So if you've thought about it, so first of all, it's a series of steps possibly you could take, but you can easily conclude, for instance, you cannot put a constant here. A constant wouldn't work. If it were a constant, I would always have a certain strain component is a constant times a certain stress component. And that constant is the same irrespective of whether I have normal or shear strain. So first of all, even in 1D, I know that the constants that govern epsilon and sigma versus gamma versus tau, they are different. One is G, the other one is E, right? So I cannot put a single constant here. There has to be multiple constants. And then you start to think about, well, how many constants should I have and in which form? And then you ultimately, based on your linear algebra knowledge, conclude that what needs to go in here such that you can relate a 6 by 1 to a 6 by 1 in the most general way possible is a set of constants that constitute or form a 6 by 6 structure, which is essentially a matrix, and we're going to call this S. Okay. Now, of course, this is the form ultimately, and we're going to write S explicitly in the case of isotropy, but this is a form that is ultimately, turns out, applicable to any type of elastic material behavior, in particular, not only for isotropic, but also for anisotropic material behavior. We're going to detail that discussion further. But before we do that, so far we've written, for instance, generalized Hooke's law for isotropy, strain on the left, stress on the right. Well, there's no reason to do that. We can certainly put the stress on the left and the strain on the right. And again, we have a similar question. Well, I have a 6x1 array of numbers and another set, and what is the most general way to relate them to another? Well, the most general way is to employ a set of constants which constitute a 6x6 structure, a new matrix, and let's call that matrix C. Now, clearly what you see here is that from these two, well, if epsilon is equal to S sigma, then I can take S and put it to the left-hand side by inverting it, and therefore I would obtain the expression for sigma, which is exactly in that form, and hence I conclude that S inverse is equal to C, or for that matter, the inverse of C is equal to S. Okay. Now, before we detail further, let me tell you what the names of these quantities are. Well, what this quantity S tells us is you impose a certain amount of stress on a material and it deforms through the action or through the properties of the material that go into this matrix S. So S and C are ultimately material properties, but which involve 36 numbers apparently, not a single one or two or etc. Okay, so you give me a load, I know the value of S, and then I get a deformation out of it. So for a given load, if I have two materials, let's say steel and rubber, if S is larger, then the amount of deformation that comes out is larger. In this case, you can imagine rubber will have a larger S because for a given load, it will deform more. So we say that such a material is more compliant, and because it deforms more easily for a given load, and therefore S is called the compliance matrix. Now, on the other hand, if we have a certain amount of deformation, and I'd like to monitor what the corresponding stress is to induce that deformation. Again, we can think of steel and rubber, and for a given amount of deformation, we can imagine that the amount of stress we need to apply to stress is larger. So we say that such a material is stiffer, so these are relative terms, stiffer with respect to rubber, and therefore this is called the stiffness matrix. And you see here the little joke that the convention plays on us. S has to do with C, C has to do with S, but that's the way life is sometimes. Okay, so we have these matrices, stiffness and compliance. Now, whenever you want to work with an anisotropic material, it turns out it has a 6x6 matrix that should be provided to you explicitly, and that matrix can be either C or S. So depending on what you like to do. If you're interested in, for a given deformation, what the stress is, you need the value of C. For a given stress, if you need what the corresponding deformation is, then you need the value of S. But we know that if we know one of them, then we can invert it and find the other one easily. So mostly in this course, as we've done so far, we put the strain on the left and the stress on the right. And so we're going to choose this convention whenever we need to relate stress to strain. Okay, so this is what we're going to use more often than that one. All right, so now we have these relations, and so you should remember immediately and embed this in your minds that these relations are valid always. These are always true. Always here refers to elastic behavior. And of course, small elastic deformations. And they can be fully anisotropic. Okay? The material behavior can be fully anisotropic, and it turns out that isotropy is a very special case, it turns out, of anisotropy. So isotropy is a simplification of a very general relation between stress and strain. And in that context, therefore, it should fit into this form as well. And in fact, we'll go ahead and write the explicit form of this compliance matrix also for the case of isotropy based on generalized Hooke's law form that we already know about. Okay, so just keep in mind that these relations are always valid for all linear elastic material behavior. So for any type of anisotropic material, they hold. In particular, they also hold for isotropic material behavior. So now what we would like to do next is go ahead and first do a small exercise where we will put the relation between stress and strain for isotropic linear elasticity into the form that we have just introduced. Now, before we do that, let me finally note the number of constants that appear, or highlight once again number of constants that appear either in S or C. There are 36 constants, right? So because it's a matrix with 36 components. So it turns out, it seems at first sight that if we have a fully anisotropic material that doesn't fit into any special form such as isotropy, then I need to somehow find out what those 36 constants are associated with the stress-strain relationship, or in other words with the material behavior, and we do that through experimentation. So we have to determine not only the Young's modulus and Poisson ratio, but actually many more constants. Do we have 36 constants? We're going to discuss that in a second.